I'm the co-chair of this session. And next, I'd like to introduce our next invited speaker, Dr. Jacob Robinson from the Rice University. And he's going to talk to us about some really innovative work on magnetic materials for miniaturized neural interface. Jacob.
Thank you, Tracy. Thank you for the introduction, and to you and Chris for organizing. And I also have to say, I'm amazed by Stephanie and her ability to immediately adapt her talk to a perfect 20 minutes. So I will do my best to follow her lead and try and stay on time. The work in my group is similar to what Stephanie described, trying to develop electronic interfaces to the body. And one of the problems that we've been working on recently is how do we make these devices as small as possible and still communicate with them, even though they might be deep inside the body. So the dream scenario might be that we have bioelectronic implants in the central nervous system, but perhaps also in the periphery. Right? If we think about opportunities for bioelectronic medicine, we might actually want to have devices that are at peripheral nerves, or perhaps in the end organs, that can both stimulate activity as well as record activity. So if we could have this kind of biological network that can both measure and record activity of the nervous system, then we might be able to develop improved bioelectronic medicines or brain-machine interfaces. And maybe, if we apply these same technologies to animal models, it helps us better understand neuroscience. So again, the dream, just think about small, as minimally invasive as possible, bioelectronic devices that could be delivered easily. And so to enable that kind of technology, you have to think about how do we communicate with those types of implants. This is a review from Paulina Anikiva's lab looking at different modalities, light, ultrasound, and magnetic fields. And of that group, magnetic fields really do the best job of penetrating through tissue. In fact, Stephanie showed some really beautiful MRIs, right? We get the ability to image because magnetic fields penetrate all the way through the body. Now, this is a little bit of a double-edged sword. The reason why magnetic fields do so well at penetrating through bone and tissue is the fact that the magnetic permeabilities are almost the same through all of these different materials. And this is different than ultrasound or light, right? Light scatters because of differences in refractive index. Similarly, ultrasound scatters at the interfaces between bone and tissues. That's how you get your image. Magnetic fields, on the other hand, essentially very weakly interact with biological tissues. And so in order for us to use things like MRIs or even transcranial magnetic stimulation, we have to have very large magnetic fields on the order of 1 to 7 Tesla. And these, of course, are large machines. In the case of an MRI, it's a room-sized magnet. So if I want to think about developing a bioelectronic network using magnetic fields, I don't want a room-sized magnet in order to communicate with it. And so this is where we turn to materials. So what we can, so the main idea is that if we have nanomaterials, these nanomaterials can have large magnetic properties, and they can convert magnetic fields into another form of energy that we can use to directly stimulate or measure biological processes. For example, if I had a material that could convert magnetic fields into electric fields, then those electric fields could directly activate the voltage gated channels. And so in this way, we might be able to use the good tissue penetration properties of magnetic fields in order to interact with biology using magnetic nanoparticles or materials. And so what kind of materials enable us to make this conversion between magnetic and electric fields? So it's a class of materials that we've been looking at recently known as Magnetoelectrics. And just as I described in the previous slide, it converts magnetic fields to electric fields. So imagine an alternating magnetic field interacts with this material, and as a result, the material generates an alternating electric field. Now, these materials have been around for roughly 50 years or so, but the Magnetoelectric coefficient here, that term that relates how much of an electric field it can generate, is typically small. So for single phase materials that were first studied, the kind of figure of merit here, this proportionality constant, is about 0.3 millivolts per centimeter Oersted, and it only really works at 20 Kelvin. So these are not really practical materials for us to make this magnetic to electric field conversion. However, if we make composite materials, either nanoparticle composites or core shell materials, we can increase that coupling coefficient, that magnetoelectric coefficient, by several orders of magnitude. And better yet, if we make laminate materials, we can increase that coupling efficiency even more. And in this way, we might actually reach levels where these materials become practical and useful for converting magnetic field to electric field, and then perhaps enabling miniature bioelectronic devices. I'm going to go a little bit deeper because we may be able to get to this later. The way that these laminates work is that it's typically two materials. One is a magnetostrictive material, the other is a piezoelectric material. And as the names imply, the magnetostrictive basically changes its strain when I apply a magnetic field. So I can basically vibrate this material if I apply an alternating magnetic field. If I can couple this material to a piezoelectric material, that strain, lambda, can be converted into an electric field. And so the overall relationship between the magnetic field and the electric field will follow the product of these two curves, the magnetostrictive curve, strain as a function of magnetic field, and the piezoelectric curve, which is the electric field as a function of strain. And now if I bias these materials towards this inflection point, I can get a very large proportionality constant here. So that's the trick. That's the physics behind it. What I'm going to do now is maybe start to take us through the process of thinking about building something useful using these material properties. So the first thing that we did is we wanted to see, can we get this thing to work in films that we fabricate in the lab? So here's an example of a magnetoelectric material that's built by Amanda Singer. By the way, she basically did most of the work I'm going to be talking about today. And so you can see this film, the electric field produced by this film is able to light up this LED. One of the nice things about it is that it's actually really robust to changes in position and angular alignment with respect to this magnetic coil that's producing that alternating magnetic field. Now the trick is that we operate this device at an acoustic resonant mode. So we want to kind of vibrate it, get as much strain as I can to get as much electric field as I can, so hopefully do something useful with it. But it really only works when I'm at the resonant frequency. And it turns out as we try to make these devices smaller and smaller, this resonant frequency approaches several hundred kilohertz. Now that alternating electric field is too fast for me to actually drive a biological response. We know neurons respond maybe up to 200 kilohertz or so. So it's really not able for me to directly drive neural activity. So what we did instead is we realized that we needed to rectify that signal. I needed to have a large voltage that was only positive and not negative, and then I could use the envelope of that alternating electric field to drive neural activity. And so here's the first example of us driving the activity. This is actually spiking HEK cells in a dish, but it's a proof of concept. The concept being that we can use this material property to drive cell activity with precise temporal resolution. You'll see here that the fluorescence changes here, which represent changes in voltage, this is a voltage sensitive indicator, occur very nicely, precisely when we turn the magnetic field on. But you'll notice what we have here are full wave rectifiers that allow us to have this nice envelope for the voltage. So that being said, we basically took this material and then we started to use this material to build a device. And then the question is, can this device actually work in animals? And so our first example of that was to show that in a Parkinson's model, we're able to achieve therapeutic benefit by creating a deep brain stimulator that was completely wirelessly powered using the magnetoelectric effect. Here, there are no batteries. I'm not going to go into the details of the model here, but if you've seen Hemin Parkinsonian rat models, you would recognize there's this rotation here in the disease state that's rescued when we turn on our stimulator. The other thing that we did is we thought, because we have these nice properties, we can make these things even smaller. And we then made a millimeter-sized device that could be completely implanted. And here what we did is we used this device to stimulate a region of the brain that makes the animal happy. It's a medial forebrain bundle. And what we did is we turned one magnetic coil in resonance with the device. We turned another magnetic coil slightly off resonance. And you'll see that this rat here pokes its head inside the coil, activates the device, starts to feel happy, and decides that's where he wants to spend most of his time. And so in this place preference, you'll see is a very strong place preference for the resonant coil. And then we're kind of mean, and then we turn it off resonance, and we turn the other one on resonance, and then the animal realizes it no longer feels good over there and decides to spend its time over in the other coil. So what we're showing is that these millimeter-sized devices effectively stimulate the brain and drive physiological responses here, both therapeutically in the deep brain stimulation example, as well as in this place preference example. So I ran through that really fast, but I want to give all credit to Amanda. What was really interesting for us is that, I started out with like this cartoon picture of kind of electric fields and magnetic fields and materials should do these things, all the way to a device that actually works in the settings that one might be worried about. As an engineer myself, I'm often worried when you put this in the animal, it's moving its head around, and maybe the angles aren't quite right. Maybe it's mechanically damped by the thing that you put it in. All the things that we had worried about in terms of making something practical were alleviated when we started to actually put this in animals. I think so. Big credit to Amanda for taking that step from a cartoon picture into a device. Now, as we did this, what we realized is this was no longer just a material. It really was, as I mentioned, a device. And so we can think about the concept a little bit, I guess, more broadly, in the sense that we're using the magnetoelectric field really, or sorry, the magnetoelectric material really as a way to create a voltage. And it's that transduction from the magnetic field that's then being fed into a circuit. So in principle, we could power any electronic circuit using these magnetoelectric materials as some kind of efficient antenna for bioelectronics. And so with that in mind, we kind of had this idea of magnetoelectric-powered bio implants, or I'm going to try to call me bits because it sounds cute. And in principle, these chips could be more sophisticated than when I showed you before. What I showed you before was just, we're going to rectify that whole wave and we stimulate the tissue. But because I have this voltage that we're generating, we can actually have digitally programmable integrated circuits that could be miniaturized to have more precise stimulation and perhaps sensing capabilities. So we began working with Kai-Wan Yang's lab at Rice University. He's a circuit designer, and his student Zheng Hao and my student Josh got together to try to build this kind of a system. So those of you who work in this space might realize that there are already devices that use magnetic fields to harvest power, and these are magnetic inductors. Right, so this is work from John Rogers' lab and the Kucherov lab. And you'll see that these magnetic pickup coils are also able to create voltage based on an applied magnetic field. And this is what's actually used today in cochlear implants and other types of biological wireless power delivery strategies. So the way that this works is that magnetic fields are generated by an external coil, and the windings of the coil here pick up the magnetic field, and the amount of voltage that I get is proportional to the area of that coil and the number of turns. Magnetoelectric materials work a little bit differently. Here, because it's different physics, as I mentioned, this thing is vibrating. So the voltage that I get is actually independent of the area. It really depends only on the thickness of the piezoelectric layer. So what a key difference is between magnetic induction and magnetoelectrics, and this was our big insight that we came to, is that as I make magnetic inductors smaller and smaller, the voltage on that gets smaller and smaller. And it actually gets smaller by a lot because I'm reducing both the area and the number of turns. So if you want to make a small device that harvests a lot of power, that creates a reasonable amount of voltage, it's very hard to do this with a magnetic inductive system. That's typically why you need centimeter scale pickup coils. So it's very difficult to make things that are millimeter sized. However, with Magnetoelectrics, because the voltage is constant as a function of area, I can make my magnetoelectric film smaller and smaller and smaller. The voltage remains the same. So fundamental difference that actually really helps us, particularly when you get to millimeter scales. So this is what it looks like. The voltage on these magnetic inductors falls off really dramatically, but it stays constant for magnetoelectrics. And so the power falls off linearly instead of cubically like it does for magnetic induction. And what that means is that at some size scale, typically around a couple of millimeters, these materials are always going to produce more power than you will get with magnetic induction. And so that actually got us really excited because it meant that this could be a fundamental way for us to power millimeter-sized devices and approach this regime where I can make things small enough to have kind of implanted bio networks. So our first device looks like this. Here's this magnetoelectric material that harvests energy from the applied magnetic field, stores it in a capacitor here, and then this integrated circuit determines what that stimulus looks like. And what's really nice about this is that it is this device is digitally programmable. So we go through this charging phase where I just turn my magnetic field on. I can then modulate the frequency of that applied magnetic field, and that causes a change in the received voltage because this is a resonant effect, right? As I move a little bit off resonance, I can actually send digital bits, and that tells my stimulator the amplitude and the timing. And then I can apply my stimulus. So we can create biphasic or monophasic stimulus pulses. This is our first generation. Our second generation has a wider window, but between 50 microamp and 1.5 milliamp. When we put these devices on rat sciatic nerve, we're able to remotely control these things. These are about the size of a grain of rice, actually, is the kind of form factor to think about. So this kind of grain of rice sized stimulator works remotely, recruits different number of muscle units depending on the amplitude that we apply. So it looks just like we would expect for a peripheral nerve stimulator. And then we started thinking what more things we could do with this, and could we be creative based on the fact that we now have the ability to miniaturize these bioelectronic implants to the millimeter scale. What kind of new things would we be able to do with it? And so we started thinking that if I wanted to reach peripheral nerve targets that were pretty distal, maybe hard to reach with traditional surgical approaches, we might be able to approach them through the circulatory system, because all of these nerves are supplied with oxygen and nutrients from the blood supply. So almost all the nerves that we might want to target are going to be close-ish to a blood vessel. So if I could get my devices into the blood vessels, I should be able to reach these nerve targets, and particularly targets in the spine where it might be difficult to reach otherwise. And so this approach of endovascular nerve stimulation has been done by a company called Synchron, but here they typically have these long leads to a traditional implanted pattern generator or one of these large magnetic pickup coils. And so our concept was that maybe we could make these millimeter-sized implants and either put them in the vessel or at a position near the vessel and have a very short lead to stimulate the nearby nerve. And as I mentioned, particularly in the spinal column, this could be useful. For example, we could go after the dorsal root, which is a common target for pain, by accessing through the segmental artery. And so we started doing this experiment. We worked with really fantastic collaborators, vascular neurosurgeons at UTMB, and we were able to implant these devices through a 11 French catheter. So a percutaneous surgical approach, which I think is super cool, right? So think about this, like you could maybe put your bioelectronic device in like an endoscopic kind of percutaneous surgical approach without an open surgery. Now we did an open surgery here because we're experimenting, but we can definitely load and deploy this thing through the catheter. And you can actually see it here. This is in the femoral vein. Oops. It's in the femoral vein. It shows up on CT, and it's a spinal column in the back and the hip. And when you can actually see it here too, and then when we actually stimulate the intercostal nerve, we can do it so strongly that you actually get chest contractions. You'll see there the chest cavity move as we stimulate this intercostal nerve. And we have our really nice controls. Like I said, this is a resonant effect. So if I tune my magnetic field slightly off resonance, this goes away. So it's not like an artifact of the magnetic stimulation or something like that. It really is mediated by our device. The other thing I want to mention is that these magnetic fields are actually quite weak compared to the MRI level fields. The field at my implant is only about 1 or 2 millitesla, so 1,000 times weaker than what you would see in an MRI. So one of the drawbacks, however, one thing, I have a couple more minutes. One thing I want to think about is that I haven't talked about ultrasound powered devices, which is a very similar approach to make millimeter sized implants. The big difference is that ultrasound is a focused wave, and it needs impedance matching, right? It needs to have ultrasound gel between my transducer and my skin. So it maybe is not the best idea for like a wearable. Here we have no need for this kind of impedance matching. Here you actually see the magnetic field coil generator. Here, this is held by the surgeons, by the way. I think Stephanie mentioned the challenge of like giving delicate things to surgeons. So another thing I love about this is that we built it, we're like, okay guys, please make this work. And they were able to do it themselves, right? So they can align the thing. And the reason why they can align it is that the magnetic fields, unlike ultrasound, are not focused. They basically apply a field to a large area. And what that means is that we have these really nice misalignment tolerances. So I can move my coil around about the diameter of a coil. So misalignments of centimeters still power my device. The other thing is I can add more devices underneath that coil, and each one of these should be able to be powered. And so this actually really approaches this, I think, interesting idea of being able to build a network. So we might be able to have multiple stimulators throughout the spinal column, different parts of the heart. Who knows? I'm not a biology person, but I just love this idea that we can have these independently controlled wireless battery-free devices. So I started to build this network. Before I play this, it gets confusing. The way that this works is that we have these independent me bits, but each one has a unique digital ID. And this is due to slight differences during the fabrication process. You can come up with these physically unclonable functions. And so I can send a digital bit sequence to tell device A what stimulus parameters to perform, and device B, and I can control the relative timing between them because they're all synchronized by the master clock. So I can have delays between these stimulations anywhere between 10 and 800 microseconds, precisely timed. And there's no physical connection between these two devices. And so what we're showing here is just a proof of concept. These are two little jellyfish that we have in the lab. We're stimulating them at the same time using two different devices. See there, we're able to synchronize the timing between these millimeter-sized implants. And as I mentioned, these are quite low field strengths, and we're able to build, well, because of that, we're able to build wearable transmitters that can be battery powered with roughly 30 hours of battery life for continuous operation. So if I need to turn this thing on, we can power something like this with a battery about the size of a cell phone for 30 hours within the safety limits of IEEE. In fact, we actually have a really high safety window for this. And so anyway, putting all these things together, what we realized is that we started with this kind of fun idea of like, this is an interesting material, and realized that it actually, I think, fits really nicely into the suite of technologies that we use to send wireless data and power to bioelectronic implants. And so I think prior to us starting, near field is a big one. We have RF, midfield, ultrasound, and light. And I think Magnetoelectrics falls really nicely into this suite of wireless power and data transmission strategies. And I think, honestly, if we, for that niche of millimeter-sized devices inside the body, there's reasons to think that this could be a big winner. We, just in a review that actually just came out last week in Advanced Healthcare Materials, we show that if we plot kind of cross-sectional area as a function of device power, already in our basically first demonstration of Magnetoelectrics, we're in a really nice regime here where we have, this is a neural dust, kind of the ultrasound powered devices, and this is Ada Poon's midfield stuff. We're already having very nice power levels. These are devices that are a little bit bigger, but we're extremely competitive in these millimeter sized form factors in terms of how much power we get. Now I put this little star here because this is unpublished data, but it turns out that the efficiency is really strongly dependent on our ability to fabricate good film. So it's not a fundamental issue like it is, let's say, for near field coupling. The better mechanical resonances we get, the more of that strain that I can transfer between that magnetoelectric or the magnetostrictive layer and the piezoelectric layer means that these devices become more and more efficient. So I'm really excited about the upside of this. And we already have devices in the lab that are kind of operating in this regime, which is, this is a log scale here, which is an order of magnitude better than what we see in other millimeter sized devices. So I'm super thrilled about applications that might be more power hungry than we typically think of for these millimeter sized devices. For example, neural recording is actually much more power hungry than stimulation, and I think we might be able to enable some of these types of applications in the future. Let's see, so I kind of started with this idea of kind of using materials as a way to go directly from magnetic fields into ion channels. We ended up with bioelectronic devices and kind of wireless power and data, but I think that's the direction we're going. There's another topic that I'm excited about, but I think we're a little short on time. So I'm going to go ahead and skip it. But to give you a preview, I think there are ways that we can come back to this concept of magnetoelectrics to mediate magnetic to electric field and think about how I can change the material properties so that I don't need that rectifier anymore. I don't need a circuit, and I might be able to create really small materials that can directly do this magnetic, convert magnetic fields into biological activity. And the concept we're looking at is a metamaterial approach. So with that, let me see, can I do that now? Great. You know, I started with this idea of how I might be able to build this network of miniature, minimally invasive implants. I think Magnetoelectrics give us a good way for doing data and power delivery. Already, I think we're at the highest power densities. I think there's a lot of room for improvement there. And because of our ability to miniaturize these devices, we were able to demonstrate the first endovascular stimulation of peripheral nerves. And for the first time in a, you know, using a, so I think it was actually the first demonstration of endovascular stimulation of peripheral nerves, period. But we happened to do it with a millimeter sized wireless device, which I think is also another first. Let's see, I want to thank the team, fantastic people. I mentioned Amanda. I think I put Caleb's picture up there also. He's a close collaborator and friend who helped us with all the in vivo experiments. You have funding from DARPA in particular to support a lot of this, as well as NIH through their HEAL award. A lot of this work is very new. So there's a list of publications here if you want to screenshot it. And then the endovascular stimulation stuff, it's not published yet, but hope to get up on bioRxiv in about a week. And again, big thanks to all these folks who powered through all this in the year of COVID, actually able to demonstrate results. So hats off to all them, and thank you all for your attention.
Thank you, Jacob. That was a fantastic talk. I think we're running really short on time. It's already 7:30. I'll just take a quick question here, and then perhaps you could also put your email in the chat and then answer their question in the chat as well. So I'll take maybe this one. It's a short question from Stephanie, actually. Are there any issues, challenges with local heating?
Yeah, great question. The short answer is no. And I see there's other questions in the chat, so I'll weave them together. The magnetic field strengths are on the order of 1 to 2 millitesla at the target typically. And that's generating something like a milliwatt or less. And so all of those are quite low. We looked at these devices under IR imaging, and we can see no appreciable change in temperature. So it's really far from anything that's going to be absorbed by the body, and the power dissipation by the device itself is quite small.
Thank you. Yeah, perhaps you could email or chat back the answers. Thank you so much for the talk.
Thank you, Tracy.
Great, thank you, Jacob and Tracy. Next up, we have Grant Tashagi, who's going to talk about dry EEG textrodes. I understand Grant is a PhD student in material engineering at Ghent University. And I believe he has a pre-recorded video. Somebody can load that up. However, he's available for questions after